Well, thank you very much for inviting me. I'm delighted to be here. It's nice to come on my first visit to Hiroshima, and I'm always delighted to come to Japan. And it's interesting to come to an interdisciplinary meeting like this where I can hear talks on topics I know nothing about. So I know that many of you are not organic chemists, so I'll try and explain the synthesis that we do in a pictorial way, and I hope you'll be able to follow it. The main theme of this talk is to try to address the question of, can we make a molecular wire? Can we make a molecule that conducts electricity a bit like a bit of metal wire? And even if you had a bit of metal wire, which is the size of a molecule, it wouldn't behave the same way as a bulk metal wire. So you get interesting quantum effects. How do those manifest themselves in a molecular wire? And what happens if your molecular wire is not a straight piece of wire, but a ring or a different sort of shape? So I'm fascinated by molecules that can mediate long-range charge transport over several nanometers, which we call molecular wires. And I think the simplest model for a molecular wire is a one-dimensional electron in a box. So that's just a standing wave. A standing wave just in a one dimension. And so for any real molecular wire, you can ask the question, how much does its wave function, to some extent, resemble a one-dimensional electron in a box? But as I said, it's often more interesting to look at rings of wire or circuits or solenoids or loops rather than straight pieces of wire. So we're also investigating molecular wire rings and asking how much the wave function of that ring resembles that of an electron on a ring, which is a different wave function from a one-dimensional electron in a box. You can make molecular wires from many different types of molecular components, but the ones that we work mostly with are porphyrins. So porphyrins are colored molecules. They're what make grass green and blood red. They're these square, flat sort of units. They're really stable molecules. They're found in minerals. They survive for millions of years in rocks. And that makes them good, robust building blocks for making molecular electronic materials. And they have the ability to bind a metal at the center. So in chlorophyll, you have magnesium. In heme, in hemoglobin, in blood, you have iron. And you can put almost any metal in the periodic table there to control the properties. You've probably come across chlorophyll in photosynthesis. It's amazing how efficiently you can transfer energy between many different chlorophyll centers. There are about, several hundred chlorophyll units per reaction center in a light harvesting system. So that means the energy is transferred very efficiently over a long distance. You get efficient long-range energy migration. But you can also use porphyrins to control charge transport, and that occurs in biology as well as synthetically. And one example of this comes in a bacteria known as Geobacter, a bacterium that's found in soil in anaerobic environments. So like most living things, this gains energy by metabolizing organic matter, by taking organic matter and converting it into carbon dioxide. But it lives in an anaerobic environment, so it doesn't have any oxygen to make the carbon dioxide. And it takes the oxygen atoms from water, and that means it generates protons and electrons, and it has this problem of how to get rid of the reducing power, how to get rid of the electrons. And so it grows filaments called pili, which can conduct the electrons away from the cell to any sink. And often this is a mineral, like an iron-3 mineral, that can be reduced. You can even use these bacteria to make a sort of battery. You can harvest the electricity and use it to get energy, not very efficiently, but you can harvest those electrons. So the bacterium creates these filaments which can conduct electricity over tens or even 100 microns. And if you look in the detail of the structure of these filaments from cryo-electron microscopy, you can see that at the center of the filament, there's often a string of porphyrins, a string of these iron heme porphyrins, which are mediating the charge transport. So porphyrins are really valuable for charge transport in biology, but we're using them synthetically to make molecular wires. We work mostly on two types of molecular wires shown here. So The top sort have porphyrins linked via acetylenes, these carbon chains, and the lower sort, the porphyrins are joined directly edge to edge. In fact, these lower porphyrin chains were first developed in Japan, in Kyoto, by Atsuhiro Asuka's group almost 25 years ago. But we've also developed them and investigated how you can use them to make molecular wires. So in these chains, you have a series of metal centers which you can change. So the M here is a metal such as zinc or nickel. And along the edges of the chains, we have these AR groups. So AR does not mean argon. It means a solubilizing substituted aromatic ring, something like this, a very bulky side chain, and that's to control the solubility. So by changing those AR groups, we can make the materials highly soluble and not prone to aggregation and easy to study in solution. If you want to know about the electronic structure of these sorts of molecular wires, it can be useful to look at the calculated band structure. And that's shown here for the butadiene-linked, the acetylene-linked chains. So you can see that we have a significant band gap in the electronic structure of an infinite one-dimensional chain, about a 1 eV band gap. In contrast, the edged-fused porphyrin ribbons have almost no band gap. So very small, almost vanishing gap here, meaning that they behave almost like one-dimensional metals. As well as the difference in band gap, you can see that you've also got more dispersion, more bandwidth, more gradient on these energy levels for the ribbons. And that means that the effective mass of the charge carrier is smaller, and you tend to get higher mobility charge carriers. One way of testing experimentally how well a molecule behaves as a wire is to connect it to electrodes and measure the conductance. So you can take a series of molecules of increasing length and measure how the conductance G falls off with the length. And the simplest model for understanding that is that it behaves as a tunneling barrier. So the conductance G falls off exponentially with the length of the molecule D, quantified by the attenuation factor beta. So we thought it'd be interesting to investigate this attenuation factor beta and see how quickly the conductance falls off with length as a measure of how well the molecule can mediate charge transport. So I started a collaboration with two groups of physical chemists and physicists, both in Liverpool and Madrid, Richard Nichols and Ed Leary. And they use an STM technique where you have a flat gold surface, you deposit a sub-monolayer coverage of your molecule, you take a molecule with sulfur end groups, the sulfur binds to the gold, you bring down a gold STM tip and measure the current as you pull the tip away from the surface. And if there happens to be a molecule bridging the gap, then you get a plateau, and you repeat the process hundreds of times to build up a histogram to measure the average conductance of a single molecule. So the plan was to do this with a series of molecules of different lengths and plot the log of the conductance against the length to get a straight line, the gradient of which is beta, this attenuation factor, to see how well the molecules mediate charge transport. So these are the histograms for the acetylene-linked linear oligomers, plotting log of conductance against distance as you pull the tip away from the surface. So here I'm plotting G over G naught, where G naught is the quantum conductance of a metallic contact. So at zero displacement, the tip touches the surface and you get a conductance of G naught, and then the conductance falls down exponentially, and then you get a plateau as the molecule bridges between the tip and the electrode, the tip and the surface, and then it breaks at a length which corresponds to the length of the molecule. So you can see as we go from 1 repeat unit to 2 repeat units to 3 repeat units, the molecule gets longer and it breaks at a longer distance, and it has a lower level plateau, meaning a lower level conductance. So from that slope, you can extract an attenuation factor of about 0.2 reciprocal angstroms, and that turns out to be a fairly typical value for many types of organic semiconductor. Whereas when you do the same experiment with the edge-fused ribbon structures, now you get a series of plateaus. They get longer as the molecule gets longer, but the conductance is essentially constant. So there's almost no attenuation of conductance with length, which is a very unusual situation. So we decided to look at longer molecules to see if we could extend that. How long can you make the molecule for its conductance to still be independent of length? So we made a series of molecules just actually slightly different to the ones on the last slide, in that the end groups now are a direct carbon to gold covalent bond, giving a smaller contact resistance, whereas before we had sulfur. We also have nickel rather than zinc, which just makes the compounds a bit more stable. And we studied this series of ribbons to up to 8 porphyrin units, as shown here. And the main observation from these compounds was that the conductance is very dependent on the voltage. So if you plot log of the conductance against the bias voltage, the voltage across the ends of the molecule, you can see that as the molecule gets longer, you have a very strong dependence on the bias voltage. The conductance is changing by several orders of magnitude as you go up to 1 volt. And you can understand why this happens, because as the molecule gets longer, its HOMO-LUMO gap, it's the gap between the full and the empty orbitals, gets smaller and smaller, and you get resonance with the Fermi levels of the electrodes. So the lowest unoccupied molecular orbital and the highest occupied molecular orbital make a gap, of which the Fermi levels normally sit in the middle. But as you increase the bias voltage, then you shift the Fermi levels until they come into resonance with the HOMO and the LUMO, and then you can get resonant charge transport and a high conductance. So we see this increasing conductance with bias, but one of the strange things that we also observe is that when you sweep the bias back again, you often get stuck in a high conductance state. So here we've increased the bias from 0 voltage up to 1 volts, and then swept it back down to 0, but the conductance has stayed in a high conductance state. So it seems that these molecules are very easily oxidized or reduced, but some of the orbitals that you empty or fill during this redox process are very weakly coupled to the electrodes, so the molecule can get stuck in an excited state which can survive for seconds at room temperature. And if we understood how to control this, it might be a useful way of making a memory device. In this experiment, we only have 2 electrodes. We just have a source and a drain connected to the molecule. We'd be able to understand more about the molecule if we also had a gate electrode at the center there to shift the energy levels of the molecule. And we can do that by making a single molecule transistor. So we use a graphene nano gap, so a gap here between 2 graphene electrodes that's only about 2 nanometers wide. We deposit the molecule across that gap, and we do that on a silicon substrate with a thin dielectric, 10 nanometer thick hafnium dioxide insulator, so that the silicon behaves as a gate electrode. So we can fabricate these devices on a chip. So this is not my lab, but James Thomas's lab in Oxford and now in London makes these chips and uses electrobeam lithography to shape these hourglass shapes in the graphene for hundreds, in this case 874 gaps, each of them with gold pads, so that they can be probed on a probe station. And you can use the probe station to apply a controlled voltage to burn a little break at the center of the constriction here. So you apply a voltage and measure the current, and as soon as the current becomes small, then you know that you've burnt that gap, and then you stop applying the current. So you have feedback controlled electroburning to just burn a 2 nanometer wide gap on all these constrictions. And then we just apply the compound from solution everywhere. There's no control, but then you can use the probe station to see where a molecule happens to be bridging between the gap. And we use molecules that have end groups that bind onto the graphene electrodes in the hope that that will encourage them to bridge across the gap. So we've done that on this linear porphyrin octamer, which has now these alkoxypyrene end groups designed to stack onto the graphene electrodes. So the advantage of the gate is it allows you to shift the energy levels of the molecule. So as you change the potential of the gate, you can stabilize or destabilize the energy levels of the molecule and bring either the lowest unoccupied molecular orbital or the highest occupied molecular orbital into resonance with the electrodes, so that you can control the conductance of the molecule either by changing the bias or by changing the gate potential. So you can create a map of the conductance of the molecule against bias voltage and gate voltage of the type shown here. So the bias voltage is vertical and the gate voltage is horizontal, and the color here tells you how well your molecular junction conducts current. So you get a Coulomb diamond pattern where these diamonds correspond to different oxidation states of the molecule. So the large white area here of low conductance is due to the neutral molecule, and then you have a diamond here from the radical cation, another one from the dication, and the one here is the radical anion. So if you look carefully at these stability diagrams, you can see some quite interesting features. If you take a horizontal stripe across the middle of the diagram here, you can see that there's very low conductance in the neutral molecule, higher conductance in the radical cation, and then lower again in the dication. If you look really carefully, you can see there's a ridge of high conductance at zero bias here. And that's what's known as a Kondo resonance, where the unpaired electrons on the radical cation of the molecule prevent the scattering of the charge-carrying electrons. So it's a quantum mechanical effect that tells us that we have coherent charge transport through the molecular device. You can also see here this stripy, you get these diagonal stripes, and these are due to a longer range interference effect, a Fabry-Perot interference across the whole junction. So it arises because the graphene just around the constriction is differently doped to the rest of the graphene due to heating during the electroburning, and you get a reflection of charge carriers leading to interference across the whole gap. Again, confirming that we must have got coherent charge transport through the molecule and through the whole junction. So when we learnt that these ribbon-type molecules have very good charge transport behavior, we thought it would be interesting to make a polymer where you have longer chains of this sort and investigate it as an organic semiconductor. So we synthesized the polymer as shown here. We've started out with a dimer with bromine atoms at the end, which we couple by Yamamoto coupling to form a linear chain with just single links here, and then oxidize it using gold-3 chloride to form the ribbon. And we have these very bulky side chains to stabilize the structure and provide solubility. And the coupling works well. You get chains of about 30 to 40 units long, and it maintains solubility so that you can characterize the material. So we'd started a collaboration with a group who used terahertz spectroscopy to measure the charge mobility in these molecular wires. So this is Misha Bond's group in Mainz. They have an experiment where you apply a short pulse of ultraviolet light to generate charge carriers, and then look at the mobility of those charge carriers on a sub-picosecond time scale using terahertz irradiation. So you get this rise and fall in the terahertz conductivity as you generate the charge carriers and they recombine. And from the shapes of these peaks, you can deduce the mobility of the charge carriers within the chain. And this showed that the DC mobility is about 205 centimeters squared per volt second, which is quite a high value compared to other sorts of ribbons that have been investigated using this technique. We also investigated another sort of porphyrin-based ribbon structure. So this is a cross between a graphene ribbon and a porphyrin ribbon. So we call it a porphyrin graphene nanoribbon. And we've introduced twists along the backbone now to increase the solubility. So this has these fjord gaps with T-butyl groups generating a chiral twist to prevent the ribbon from being planar to make it more soluble. So we synthesized this polymer, quite similar route to the previous synthesis I showed you. It's Yamamoto coupling followed by fusion, Scholl reaction, to fuse all the aromatic units together to form this ribbon. We don't control the relative stereochemistry of the twist. So although these are chiral twists, we have a complex mixture of diastereomers. But we have made shorter oligomers, which we've resolved into enantiomers. So this dimer, for example, you can separate the two enantiomers by chiral chromatography, and then look at the circular dichirosm spectrum. So they are chiral units, but in a long polymer, we don't control the chirality. You'll have mixtures of twists in different directions. So we also measured the charge mobility by terahertz spectroscopy in these sorts of ribbons in just the same way that I mentioned a moment ago. It's a smaller mobility. It's about 30 centimeters squared per volt second in this case. So if you compare these results to some of the other graphene nanoribbons that have been investigated using the same technique, you can see that particularly for the porphyrin ribbon, it's a very high value. 200 centimeters squared per volt second is one of the highest mobilities that have been studied for these sorts of ribbons. But the values on the whole are similar to that of a range of different graphene ribbons. But I think the exciting thing about the porphyrin structures is that they're very versatile. In these cases, we just have nickel as our central metal, but we could put almost any metal in there and use the magnetic or electronic behavior of the metal to change the properties of the ribbon. So that's a little introduction to the linear molecular wires that we've been working with. Oh, actually, I'll just talk about the helical one. So recently, we've also been investigating a helical structure, which I thought is particularly relevant to this meeting, where we have two porphyrin chains. The one shown in blue that has mesopyridal groups that create a chiral framework for binding a fully pi conjugated butadiene-linked strand. And if you look down the end, you can see that we have 6 repeat units in one pitch of the helix. So we've just started investigating these sort of helical structures. And we've investigated the trimer, as shown here, and shown that you can get a strong circular dichirosm spectrum for the trimer in the same regions of the absorption spectrum. I think this is an interesting way of making a molecular solenoid or helical molecular wire. So moving on to the rings, the first question about a molecular wire ring is how do you synthesize it? How do you take a molecule that would like to be stretched out straight and force it to form a ring? So to do that, we use templates. So template is something like the wooden framework that would be used to make an arch when you're building a cathedral. And as you hold the building blocks in place while they're cemented together, and then when you have the final archway, you can remove the stone building blocks. So if we want to make a molecular wire nanoring, such as this 6 porphyrin ring, we need a template which can coordinate to the 6 zinc centers to hold the building blocks in place. So we do that here using this hexapyridal template to hold these zinc porphyrin monomers in place while they're bonded together using palladium catalyzed coupling to form this nanoring around the template. And the crystal structure just shows that you have the regular curved pi system all the way around the central template. You can easily remove the template if you want, either by adding acid to remove the zinc centers or by adding a competing amine ligand. So we can use larger templates to make larger rings. We can also use small templates to make large rings if we have a mismatch between the number of binding sites on the template and the building block. So this is known as the Vernier principle. If you have, say, 6 binding sites on your template and 4 binding sites on your building block, you get a ring which has the lowest common multiple of 4 and 6. So in this case, you get 12 zinc centers in your product. You get a figure of 8 shape and 12 zinc porphyrin units. And the crystal structure just confirms that you have that tightly folded figure of 8 shape. But if you remove the templates, it springs open into a regular circular molecule. And you can see that from scanning tunneling microscopy by depositing on a gold surface. So these are STM images of the 12 porphyrin nanorings under UHV deposited on a gold surface sitting on this step edge. So we can use template-directed synthesis to make a wide range of these molecular wire rings. But the next question is what is their electronic structure? So I said that the wave function of an electron on a ring is very different from that of a one-dimensional electron in a box. So it's different because in a one-dimensional electron number box, you have the lowest energy level, which has no nodes, and then the next level up has one node, and the next level up has two nodes, and each of those energy levels can just take 2 electrons. Whereas an electron on a ring, you have a lowest energy state, which has no nodes, and then you have 2 possible states with one node in orthogonal directions, and then 2 with 2 nodes, and 2 with increasing number of nodes. And so that means that you can have 2 electrons in the lowest energy level, and then 4 electrons in each of the other pairs of degenerate levels. And this leads to something known as the Huckel 4n+2 rule, which guides the electronic structure of a delocalized ring, and shows you that if you have 4n+2 electrons, you have an aromatic structure. So in a molecule like 18-annuline, shown here, you have 18 4n+2 pi electrons, and that leads to an aromatic structure, which means that it can sustain a ring current when placed in an external magnetic field. And the ring current flows in such a way as to oppose the external field inside the ring. So this induced current shields the inside of the ring from the external magnetic field. And you can easily see that this is happening because in the proton NMR spectrum, the proton on the inside is shielded at -3 ppm, and the one on the outside is deshielded at +11 ppm. So nuclear magnetic resonance provides a very sensitive probe to magnetic effects and tells you that you have these ring currents in the molecule. And any molecule that has completely delocalized electrons and 4n+2 electrons should have an aromatic ring current, whereas if it has 4n rather than 4n+2, you get a ring current in the opposite direction. You get the opposite pattern of shielding. And one thing that fascinates me about these aromatic ring currents is that you have a similar effect in non-molecular rings. So in mesoscopic structures, like this ring of aluminium, as long as it's at low temperature, so the coherence length is greater than the circumference of the ring, if you place it in a magnetic field, you get a ring current which is not dissipated, even though the ring is not a superconductor. The lowest quantum state of the system has this persistent ring current, which is just like the ring current of a molecule, except that this sort of ring current changes as a function of the applied magnetic field. So it changes in magnitude and direction as you change the external field. And no one has seen this sort of oscillation in a molecule. And the reason that it's difficult to observe in a molecule is that the flux quantum B0 for one oscillations is inversely proportional to pi r squared, the area of the ring. And molecules are very small rings, so they would require a very large magnetic field to get one of these Aharonov-Bohm oscillations. But I hope that perhaps by investigating large molecular wire rings, we might see these sort of quantum mechanical effects. So if we look at one of our nanorings, molecular wire rings, we can put fluorine groups on the template so that we can probe the shielding inside the ring using fluorine NMR. But we never see any ring current in the neutral molecules. So we see little local ring currents. There's a little local ring current in each individual porphyrin, but we see no global ring current in the neutral molecules for any of the rings that we've investigated. But if you change the charge on the molecule so it's not neutral, then you can start to get a ring current. So we change the charge Q in this experiment from neutral 0 to 6 by adding this oxidant in solution to just take electrons away from the whole molecule. And if you look at the nuclear magnetic resonance spectrum, in looking at the fluorine, the fluorine nuclei, you get a series of spectra shown here. The green vertical line is the chemical shift of the reference template on its own. You can see you get a small shielding in the neutral compound due to the local ring current effect, but there's a much bigger shielding in the 2+, and then a deshielding in the 4+, and a shielding again in the 6+. So this change from shielding to deshielding to shielding tells us that as we change the number of electrons, we're establishing a global ring current and changing the direction of that ring current as we go from 4n+2 to 4n to 4n+2 pi electrons. So we can see a similar thing if we look at a 9-porphyrin ring shown here. So again, it has a template with fluorine groups on it. And we look at different charge states. We're adding oxidant as we go from neutral up to 9+. And you can see this shift as you go to the 4+ being aromatic, the 6+ being anti-aromatic, and 8+ being aromatic again. And in this case, just to check that we're really looking at ring currents around the whole molecule, we thought we'd synthesize a system where we have a break in the ring. So in this complex, it's almost identical, but it's not a ring. We've got a break. So it's just a split ring or a loop. And now if you do exactly the same oxidation titration, you don't get any of these shielded or de-shielded signals showing that you need a proper ring to get a complete ring current. So going to larger rings, the largest one in which we've seen very clear ring current effects is this 12 porphyrin ring, which we investigated with a stack of 2 templates. So the role of the templates now is to hold the whole molecule in a circular shape. And if we do the oxidation titration, we look at the fluorine groups on the template. Again, we get shielded for 6+, de-shielded for 8+, shielded again at 10+. So that tells us that the 4n+2 rule works reliably up to 162 pi electrons. If we go to larger rings, such as, before I go on to that, I'll mention the change in the shape. So with these rings, we can change them from being circular to being in a figure of 8 shape. And if you have the figure of 8 shape, you'd expect that one loop would have the opposite effect to the other loop. So if you think about any ring current induced in this loop, it's going to be equal and opposite to the ring current in the other loop, and the overall effect should be 0 ring current. So just by changing the shape of the molecule, we can change the way it interacts with magnetic field. And that's exactly what we see experimentally. So in the big circular ring, we get strong ring current effects, whereas in the figure of 8 shape, we get no shift in this signal, no evidence for any ring current at any oxidation state. Moving to the larger rings, the largest one that we've tested for ring currents so far has been this 18 porphyrin ring. But in this case, the evidence for a global ring current is very subtle and not totally convincing. You get very slight shifts. But I think now we've made such a large ring that we probably haven't got coherent delocalization all the way around the ring. So we need to make rings that have stronger electronic coupling. So obviously, from the first part of my talk, this means we should look at edge-fused belt-type structures rather than the acetylene-linked ribbons. So this is a theoretical paper on the electronic structure of these fully edged-fused nanobelts. And these are predicted to have ring currents even in the neutral form. If you charge them up, they have ring currents which are stronger and extend to larger rings. But even in the neutral molecules, they're predicted to have global ring currents which are significant up to 24 porphyrin units. So this plot shows you that the predicted sign of the ring current changes as you go from 6 to 7 to 8 to 9. As you change from odd, if you change to even to odd, you change from anti-aromatic to aromatic until at least 24 porphyrin units. We have now just started investigating these belts experimentally, but I don't think I've got time to tell you about that today. That will have to be saved for another lecture. Just before I stop, I should say that one of the reasons why we're excited about seeing ring currents in these large rings is that it means you have coherent delocalization. You have a wave function similar to an electron on a ring. And that means if you connect these molecules between electrodes, you should get coherent charge transport. You should be able to switch between constructive and destructive interference by applying a gate electrode or applying a magnetic field. And recently, we've collaborated with some theoreticians to show that it should be possible to use the magnetic field to switch the conductance of this sort of ring, even if the flux passing through the ring is much less than a flux quantum, as long as you have very weak coupling to the source and drain electrodes, so that you use the magnetic field just to shift the energy levels so they go in and out of resonance to the Fermi levels. So those are all the results that I wanted to present to you. I hope I've shown you that porphyrin-based molecular wires can display truly wire-like behavior, both for linear rings and for cyclic rings. If I look at the title of this symposium, I'm afraid I've said nothing about sustainability or knots, and I've only briefly mentioned chiral materials, and I'm not even quite sure what metamaterials are. But I thought it's just possible that this work might be relevant to metal materials, even though I don't really understand them. I know that you can get these split ring resonators, and you can make metamaterials which can change the refractive index in an artificial way to microwaves by using small, millimeter-sized or split ring resonators with this sort of structure. And I wonder whether if you can control molecular wires, make wire-like structures and split wires on a molecular scale, maybe you can make metamaterials that work at shorter wavelengths. But you need to tell me about that. I don't know about that field. But thank you very much. I need to thank these people for all their work. And thank you very much for your attention.